I hope we caught it right this time. This is going to be a presentation split in two parts. I'm going to do the first one that is a bit more conceptual, you could say, and then directly, because we've seen that now we're in the program directly in front of the session that will deal with laboratories. So Anna is going to spend quite a bit of time to talk a little bit about the stuff that we've built, and maybe that's interesting or inspiration or something like that. We hope so, at least. I will start with giving a little bit of an idea why we're doing this, or why we're doing what we're doing, where we're coming from. And as you've seen, we are from Denmark. Denmark is a bit of a strange, or a bit of a peculiar, in a bit of a peculiar situation, because the power system has actually changed very, very rapidly and quite dramatically in the last 2 or 3 decades. We used to have, so in the 80s, we used to have a system with roughly 15 big coal-fired power plants. That was our power supply. 20 years later, that was 2001, there were a lot of, that's the little green dots that you can see here, a lot of small CHP plant, combined heat and power plants that are used for district heating in small towns. As about 500 of them were built, because there was a political climate that was simply giving subsidies to those or giving favorable conditions for those to promote energy efficiency. Because obviously, if you have a thermal power plant and you can't get rid of all the waste heat, then you have a lower efficiency than if you can heat houses with it. So large parts of, Copenhagen, where I live, that's I think 95% of the buildings are on district heating, actually. So just using a lot of the thermal waste energy that comes from the traditional power plants. But what has also happened, and that's probably the most dramatic one, is that in 2001 there were about 5,000 wind turbines. That's given that there's only 5 million inhabitants, and our peak load is about 4 to 5 gigawatts, something in that direction. It is actually quite a lot. And so that development hasn't really stopped. We just got a new government last September, and they have increased the already ambitious targets that the previous government has had. So now the energy plan is to get 50% wind power in 2020. Currently we have, I think 29 was the latest figure I heard. And there's several offshore wind parks in the pipeline, so we all assume that we're going to reach that target. That's in 8 years from now. That's not very far. There's also something else happening, and that is, there's something, anyway, that is something that's relatively new. About last October or November or something like that, we did not really have a lot of photovoltaics because we're quite north, and we didn't have any generous regulation, generous subsidies like the Germans had, for example. But suddenly the prices came down enough so that things started becoming economical. So about last autumn, we started going into an exponential development for photovoltaics as well. And Dansk Energi, which is sort of the association of the distribution system operators in Denmark, they have just made some scenarios for where they expect photovoltaics to be. And sort of in the medium scenario, which I think is actually too conservative, there's going to be about 10% PV in 2020, and that's not even in the grid plannings yet. So we can assume that in 8 years we're going to have 60% renewables in the grid. That's a little bit, that's also why I would like to contradict a little bit what you said, that at least for some countries, yes, we have a crisis, and Denmark is also noticing the crisis, even though we come down from a very comfortable economic situation. But our grid operators, for about the last 5 years, they started getting, they started really changing their attitude on what they have, where they're at now is that, well, if we still want to run our grid in 10 years, then we need to do something now. So I think smart grids is more a matter of how than a matter of if. And there will be funding for it, and there's a lot of interest for it. So for some countries, I think Germany is probably in a similar situation with the nuclear exit. That the pressure of the facts that there's a political will to move the power system towards high penetration of renewables, decentralized production, large number of electric vehicles at some point in the future. The political pressure simply makes things happen as well. So it's not only the economics. Yes?
So, is it really, so there are no subsidies and it's still
No, there are no dedicated subsidies like in Germany. There's a net metering setup where for up to 6 kilowatts installed system size, so I mean that would be typical household PV, a bit smaller than the average German PV side. You can get up to the amount of kilowatt hours that you consume in a year in your household. So you cannot have net positive generation over the year, but you can sort of for the amount of energy that you generate that compensates for your household consumption in a year, you basically get the full power tariff as a refund, and for everything that goes above that, you just get the market price, which is about a third. But sorry.
So it pays by the rule from now on.
Sorry, say that again.
So with this regulation,
yeah,
it means that since 2011, it actually pays off. Otherwise, it wouldn't work.
Yeah, it started, I mean, there's always a thing of when do people get interested in it. So there was when the newspapers also started talking, oh, this might be a good investment now. I think actually it would have been a bit earlier, that probably as late 2010, because I mean, the PV prices have been dropping dramatically. That would have been interesting, but I mean, you can see, we just had latest figures from Danske Energi that I think they process about 150 applications for a PV system installation a day right now, which I mean, again, we have 5 million people living in the country, so this is it's quite strong. And if you also look at what the German curve looked like 4 or 5 years ago, then yeah, so I mean that's kind of my assumption that we are there where Germany was 3 or 4 years ago or something like that with respect to growth. So I think, yeah, or also other people think. I mean, as I said, there was just this recent study that was published a month ago that assumes some scenarios. Even the very conservative scenario actually assumes a significant growth of PV to several percent by 2020. This is a curve of the wind power production in Denmark. This is megawatts. And the demand in Denmark over a period of a whole month in January 2008. The winter is typically where we have the highest wind power production because of the storms. Winter is also where the demand is high, so that doesn't match so badly. But that was in 2008 when we had slightly more than 20% wind in the system. So if we just assume that we would add, and this is the western part of Denmark, I also have to say we have 2 power systems. One of them is connected to the continent and one of them is connected to the Nordic system. And until last year, they weren't actually electrically connected, so they could only indirectly exchange energy through Sweden or Norway or something like that. So now we have actually the Great Belt has been, the DC cable has been provided between these 2 systems, but since they don't share the same frequency, they are kind of independent control areas. So this is for the western part of Denmark, where also the majority of the wind power is installed. And so if we just project, and that means adding 3 gigawatts of wind power for the 2020 scenario, and just do the dumb projection by just scaling up the wind production with this factor, you would see that for actually quite a significant amount of time, wind power production exceeds demand. And you can even see in the 20% scenario, we already have a day where wind power, or some hours in a day where wind power covered more than 100% of the country's demand. And right now, well, obviously, I mean, we're integrated into the European grid, so we're solving that by sending it to Germany or sending it to Norway and then buying some of it back when the wind is low. But if you have these, the problem is everybody wants to use that capacity. I mean, the Germans are also building a lot of renewables, and the Norwegians, everybody's building cables to tap into the Norwegian hydro reservoirs. So that. I mean, as this develops, some of that we will have to cover ourselves. And if you don't do anything, if you just run the system as it is right now, you would simply have to tell wind turbines to shut down for a significant part of the time, and that's very expensive, obviously. So, yeah, I think in that scenario, I think that's a simple simulation. That would be more than 1,000 hours a year. That's would not be very. Oops. Be very good. So something's wrong here with the layering, but anyway. So if we project this, you know, I had 1981 and then 2001, and let's look at 20 years later. What have we added? We have added all the little small dots, small energy resources. I don't think that's an official term, but that simply covers all the parts of the grid that are already part of the grid, but they're not participating in the control of the grid yet. And that is mainly the whole demand side, as we've heard a long presentation about yesterday, in households and industry, but it also covers, for example, small photovoltaic generation, or micro CHP, or electric vehicles, or heat pumps, and so the challenge is to, because the thing is, if we get 60% of our energy covered by renewables, then obviously the big power plants, they're only covering 40% of it. And traditionally, in power system operation, we rely on these power plants to provide all the services that make the grid run, balancing power in particular, to make supply and demand match. And so if the role of those is decreasing, that will have to come from somewhere else. And where else should it come from than from all the other units that are taking over? So that's, I think, pretty much consensus that if we want to run this grid with such a high penetration, and I don't think it's the end, because the energy plan actually says more than 80% penetration in, I think, 2050 or something, then we will simply have to use all the resources that can play a role. But that means we have many, because the system that runs, the control system that runs this power system, it was designed for handling and coordinating 15 power plants, and not for 1 million or whatever else the number is going to be. It's going to be very high in any case. So, so that's basically the background of our work. We take this as given. Wind power and PV is going to be there to a large extent. We will need to make these. We will need to activate these resources. Means we will have to be able to communicate to them. We will have to be able to coordinate them to get system services out of the whole thing. So, what kind of interactions do you have between small distributed energy resources and the grid? Sorry, DER. I don't know if everybody knows the term. It's a distributed energy resource. So that's it's a bit of a wide term, but it typically covers, in the meaning that we use here, smaller units that are connected to the distribution grid, as opposed to the traditional big power plants. What kind of interaction do you want with them? You want to do some data acquisition, and here we're talking real-time data acquisition, because this is to get the power system state. One of the main problems right now in grids is that you have full information about what happens in the big transmission grid, but if you go down to the household level, to 400 volt level, or to even the level above 10 kilovolts, there's not very much information. I mean, we talked to one of the utilities in Denmark. They said, well, all we have is on some selected feeders in our 10 kilovolt network, so the second level from below, we have some current measurements. So no voltage, only current. And they don't have a sign, so they don't know which way the power flows, because traditionally you didn't need to know, because the power was always flowing down to the consumers. So now they have these old instruments, and it's very expensive. I mean, substation equipment for 10 kV, that's already quite expensive. If you go to higher voltage levels, it's even more expensive. But the problem is somehow we need, if we want to do intelligent control down there, and we want to, because the only alternative to intelligent control is to invest massively in putting more copper in there, and that is also very expensive. Then we need to get this information from somewhere else, and one obvious source would be small resources out there. I mean, if you have a photovoltaic inverter in your household, it already measures frequency and voltage of the grid and other parameters, because it needs that for its own operation. So, but right now there's no way of collecting that and actually making it possible to use that in power system control. The other thing that you want, I mean, that's what I talked about earlier. You want some ancillary services or system services that these units should provide for you. One of the main ones is frequency control. So that's the power balancing itself. You also want to have a bit of a margin in case something bad happens. So you might want some units that are actually that you can take off the shelf very quickly in case you need some reserve capacity. You want to do voltage control. That's mainly a problem in distribution grids. If you have a very long line and at the end there's some big consumer or big PV plant or something, that you run into problems to provide the power quality that you have promised to your customers. And then there's a few other things. I just named one as an example. Well, if the grid goes down, you also need to sort of start it up again. And right now that's a very, very long process, because it's all done manually, and you have to be very careful, because you can't just start one generator and then smack all the load in the grid back on again, and then the whole thing blacks out again. So you have to step by step, okay, we start this thing, and not all generators can start on themselves. So you start this thing, and then you add a bit of load here, and then you check, and then you add some more here and some more there. And so in principle, right now this is features that big power plants are doing, but because obviously the small ones will have to be able to do it as well if they're taking over. The other thing that you have to do is some business operations, and one of them is an existing function, metering, because you will still have to pay for your power. So power companies or utilities, they would like to still know what you've been doing. That gets even more complicated if you're actually starting to provide ancillary services, because they're usually being paid for. That's the whole motivation. But it also means that there needs to be some proof that you actually provided that service that you were paid for. And then, as has been mentioned several times in the last 2 days, most of the operations these days, they interact with energy markets because the markets have been liberalized in Europe. So there will have to be some, if decisions are taken down at the level of small units, then they will also have to somehow be able to connect to energy markets. And then, so this is basically what, it's a bit simplified, but that's basically what the control structure or the sort of the basic fundamental architecture of the grid looks like today. So you have a central control room. There you have an energy management system, EMS, that consists of several services, several applications that are running. And you have a SCADA system, supervisory control and data acquisition. That is the thing that moves mainly, its main function is to move data back and forth between the different parts of the grid. And then you have some units, mostly out in substations or in power plants. You can, some of them are called RTU, remote terminal units. Some of them call intelligent electronic device. But basically what you can see from this, and this is also where it comes from, when automation was introduced into the power grids at that level in the 50s and 60s, this is factory automation, right? So the same structure that you had with classical PLC factory floor systems, except that this one is a wide area system that spans the whole country, so it's not confined to a factory. Also, the difference here is that now we want to, in a factory, you know, you have 100 units that you want to control. Now we want to go and scale this to 1 million. So, and the assumption is, well, this is not going to be trivial to scale this, so you can still run it from a central point. There's also some, particularly if you want some robustness in the grid, that, for example, parts of the grid can survive in case of a blackout, then this is maybe also not the most optimal structure. And obviously there's a single point of failure. I mean, the real grids, they have duplicate entities of some of those, but I mean, that's just a single point of failure with a switchover, so it doesn't really. If we go to the other side, what's been the vision when I started going into, or when sort of the whole smart grids thing started a couple of years ago, there was one sentence that you heard a lot that was like, yeah, we should do electricity like the internet. And I think we also, we like that idea. Yeah, that's cool. There's a lot of super technology out in the internet and we should modernize this and so on. And that was kind of the bit naive vision that we had initially with the project that we did back then. Yeah, well, intelligence completely distributed and they just all talk to each other. That's also what you hear a lot in an agents context or so. Yeah, agents was a big word back then as well. There's sort of two observations of this. One is there's one trivial way or one relatively simple way of implementing something like that, and that is where you have a globally observable quantity, because then you don't have the communication problem. And that exists, it has been existing in grid for decades in a feature that's called primary frequency control. That is what happens if you have a disturbance in the grid, what happens in the first milliseconds and few seconds, that all generation units, they simply watch the frequency, and they have a curve that's called a droop curve, where they simply have a characteristic of power versus frequency. So if they see, for example, the frequency goes up, which means that there's too much generation, too little consumption in the grid, they will reduce their output and vice versa. And that's kind of a very simple self-stabilizing first aid, band-aid thing that the grid is doing. It's easy because the frequency is the same all over the grid, but that's also pretty much where it stops. So if you have some global coordination that you cannot do via this single observable quantity that's there, that it gets more complicated, then units need to communicate, and then you run into all kinds of scalability problems with a fully decentralized system like that, because if either you start forming groups, which in itself is not a trivial exercise, or you will have to use broadcast communication, and then you have a problem that the communication needs grow n square or something like that. So, and the other observation is that there's not much of a point in decentralizing a single function in the grid if that function depends on other things that are centralized, because then you don't, the things that you want to achieve, like more robustness and better scalability, then you are still not very much further. So in principle, and it's something I said yesterday, that the obvious way to me would be to start looking at the lowest level tasks that everybody else depends on and look at what you can do with those. But as a compromise, or that's kind of something that we arrived on a little bit, a classical solution to scalability problems is that you introduce a hierarchy where you have several levels, and then everybody has a master, and you have a limited number of units that talk to one master, and then you have some masters that talk to a higher master, and so on. So that's a classical divide and conquer approach. It can give you some scalability. It's not fully decentralized anymore. For many functions, and there's actually quite a number of projects that are looking at different types of aggregation. I will go into that a little bit in the next slide. For many power system functions that are needed, or for many ancillary services that are needed, you can actually relatively easily show a way how you can solve that with aggregators. The only problem is, and it was also mentioned earlier, that there is no, the grid is dynamic, and if the aggregation hierarchy does not follow that dynamics of the grid, then you will run into problems because you don't really know what you're actually aggregating and what kind of functions you're providing where in the grid. There are basically three concepts, you can say, that are pretty common about aggregation. This is, you can say, the copper hierarchy of the grid, so from the highest level transmission to the lowest level where the households are connected. It's a very simple graph, and sort of there are three concepts that you see a lot that are also being demonstrated, that are being researched on quite a lot. You might have heard about VPPs, virtual power plants. That is basically a very simple aggregation method where you say that you take a number of units. Most of the time they're going to be equal or units with a similar functionality. You don't look very much on where they are located, because what you're really interested in is providing services somewhere up in the tree. So you just also use the copper aggregate, you can say. There's another concept that has been discussed yesterday, that's microgrids. That's typically where you look at the lowest level, or maybe the level above, and you try to have parts of the grid with relatively few components that can function as a separate grid in themselves. So in principle, they are able to disconnect and reconnect to the grid, and maybe do a complete energy balancing inside their confines. And then you have a concept that is the only one that I know is what Energinet, which is the system operator in Denmark, has been playing with for a couple of years, which is cells. So you do the same thing with actually a larger portion of the grid. And the difference between cells and microgrids is that for cells, you disconnect from the grid in case of an emergency. And for microgrids, this might, well, depends on who you ask, but this might be part of the standard operation. Then there's a couple of things. What do you need if you want to use aggregation, or if you want to implement aggregation? And this is a little bit, oops, there's a menu that came up. And there's a little bit some pieces of wisdom that kind of came up as part of trying to implement this, trying to implement some concepts in a lab setup. That's a pretty obvious one, that if it gets much easier if the units that you aggregate are the same or at least similar in function. So if you have a whole menagerie of things that are very different, it gets very difficult to make meaningful aggregation functions. It's particularly difficult when you try to later add new types of units to your system that you didn't know, or whose behavior, whose properties you didn't know at the time that you were writing the aggregator. And that also creates a difficulty for discovery. So if you want some features that are, you could label plug and play, where you have new units that just find their space or find their spot in the grid on themselves. If your units are too dissimilar, it is also very, very difficult to do this. And right now, the way that communication works between units in the grid, well, you have communication is based on the data model, and the way that data is structured in the concepts in the data models that are used at the moment is that these data models, they are separated by type of unit. So you have a data model for wind turbines, and you have a data model for PV, and you have a data model for hydropower, and so on. And the problem is that doesn't really help aggregation if you want to add dissimilar entities together. So that's a little bit the simple version. What's 3 wind turbines plus 5 solar cells? And if you really want to make aggregation easy, then distributed resources, they should be able to describe the function that they have in terms that are ideally constant over time. And what could that be? That's a bit of an illustration of this. If you have an energy resource and it has a communication interface that you want to use to talk to it, and that communication interface is specific to a particular type. So we have here, the red ones are resources of type A. Let's say that's wind turbines, for example, or you have a resource of type B, that's photovoltaics, because that's the way it's structured right now. What you need is, if you want to aggregate these and get a common service out of, let's say, 100 different units, you need to have sort of modules or adapters or something like that in your aggregator for every new unit that you get. And the problem is if you now get a resource of type D because somebody came up with a new energy technology, latest example could be electric vehicles, for example, you need to at least extend this, in the worst case, rewrite this. So a much better way of doing this, in my opinion, would be what you really want. You're not really interested, that's this wind turbine that is providing your ancillary service. What you're really interested in is this unit can help me balance the power, or this unit can participate in voltage regulation. You don't, all the specifics about a particular unit you're not really interested in. So what you really want for these kind of energy management system applications is actually communication that is based on services that these units can provide. Because then you just have an aggregator for the service that you want anyway, and then you can add resources to them as long as they implement this interface. That has also one advantage, that right now it's the problem of whoever writes the aggregator to make the mapping to all the peculiarities of all these different components. If you force somebody to have a service-based interface implemented in the resources, you basically make it the responsibility of the person who has built the resource to make the mapping. And that's much more ideal because they usually know much more about what the resource is and what the mapping could be like, right? If you do aggregation, there's also, well, if you want to do control, obviously you have to close the loop somehow, so you have to go both ways. And it's usually aggregation the way up. If you just collect data, that's, in most times, that's pretty similar. It's pretty simple because quite often you just average or sum or do something like that. If you go the other way, if you distribute control signals, deaggregation, you often have to do something like scheduling or queuing or dispatch, which can be a lot more tricky. And the other observation is if you want to have this scalable also to the term that you, for example, can add more layers at will. In principle, you have to make sure that you use same or similar aggregation functions at all levels of the hierarchy, because otherwise you need to treat the levels specifically, and that doesn't really help. There's a problem that was already mentioned earlier that is keeping us updated, because we have two topologies in the system. One is our copper topology, that's the one that we deliver the service through. And then we have a communication topology, that's the one that's used to maintain or to administer the service, you can say. And if they are not, you can say, if the system is not aware of both of them, in particular not of the copper topology, then it can be very hard. Let's say you want to do voltage control in a particular feeder. And what if the topology changed? Distribution system doesn't change its topology very often, but it happens, particularly when there are faults. Then parts of the system might be switched to another part of the system. What is happening if your aggregator is not aware of that? So suddenly you think you provide your services in one part of the system, but it's actually connected to another part of the system. You could make things worse. So there has to be a thing, and we discussed about that earlier in terms of topology tracking. That's not the only application of it, but it's one of the applications of it. You will have to make sure that at all time you know where you are, and it's not really trivial because the grid is so complex, and for many services that you want to provide locally, you will also need that information locally. Right now, topology is something that is provided in a single database at the system operator, but that's not necessarily where you need it if you want to do something distributed, if you want to get your intelligence out of the system operator's headquarters or control room. There's one more aspect, and I have another aspect, and then I'm done, is that the way that systems are, as I said, the paradigm that's being used is very much factory automation, or factory automation 1960s. And in factory automation 1960s, communication is synchronous, and you assume that your communication is reliable, and you have bandwidth, and you have a defined latency because you lay a wire to the unit that you're talking to. And that's also how power systems pretty much work today. If you build a very expensive coal-fired power plant with a couple of 100 megawatts, then it's completely irrelevant if you have to spend some extra for laying a doubly redundant glass fiber to it from the control room. But if we're talking small distributed energy resources, the margins of money that you could make by providing system services, one of these things, they're so tiny. We're talking about a couple of euros a year maybe, that rolling out some dedicated communication solutions I don't really believe in. So probably a lot of these units are going to hop on existing DSL lines. I mean, that's also what you see in some field tests these days. People just get a gateway for their home DSL router. And but then the whole thing changed because we don't have a reliable communication anymore. We don't have the bandwidth. We don't have a latency that is defined, so we don't know when the device is going to react. And particularly, we don't have much experience how it will react in case we have a partial system blackout, for example, that might also affect the power supply of communications. So what we actually want is, if we're talking, that could be to a supervisory controller, or it could also be in a more decentralized setup where units talk to each other. What we actually want is a more asynchronous type of communication, and the ability of units out there to at least go to a defined state or do something or still continue doing something meaningful in case you lose communication, because right now that's not thought into the system really, not very much. And the final issue, I'm not a big expert on that, but it's an obvious one. If you put programmable systems out into consumers' homes by the million, somebody is going to hack them sooner or later. We've seen that with all other technology where that has happened. And we've also seen that all the existing systems with reasonable cost to provide authentication and to provide sort of secure identification of a user and things like that. SIM cards, for example, are a good example. It's a matter of a couple of years, and then they will be overridden, or somebody will find a way of getting around them. So since this is a system where basically everybody depends on everybody, and if you could, for example, imagine somebody setting up a botnet that controls 1 million PV plants or a fleet of electric vehicles or something like that. I mean, that's definitely not out of the reach of imagination these days. You would have to find a way of stopping that, and for that to happen, you would probably, whatever system you design, you would have to put both authentication and verification of, like, filtering out false tickers or something like that in pretty much all stages of an aggregation hierarchy that are in there. That was a bit sort of the abstract side of this, and I think I'm handing over to Anna. How much time did I use? A lot? Damn it. Good.
Just a comment.
Yeah.
To the last point, the current security measures, I'm less optimistic than you are,
Okay, good.
Are not even used, I think.
Yeah.
Okay, so now we switch to practical stuff. I want to talk about more practical. I want to talk about our lab for research in distributed systems. We call it SUSLab. And I'm Anna. I'm a postdoc at Technical University of Denmark. And I work together with Intelligent Energy System Group. And we have this facility for our use at DTU. So first of all, where are we? We are just off Copenhagen at this site. As you can see, our university is quite spread. This is the main campus in Copenhagen. And our lab is also where we are, just close to Roskilde. And the laboratory is for intelligent distributed power systems. And it's a place that we can both research and test different concepts and strategies for control of distributed system and for integration of a number of distributed energy resources. So what we have a small real-world power grid that consists of 2 wind turbines, 10-11 kilowatts, 3 PV arrays that are distributed in different locations. One is here, and one is on the rooftop of this building. And there are different technologies as well. We are also looking at the components, how do they behave in different conditions. We've got a diesel generator, we've got an office building that has actual rooms and heaters, air conditioning, lights in it. We've got a dump load if we want to simulate something in the grid that we can actually consume power in one point to make it more realistic. 3 mobile loads that we can connect in different places. Flow vanadium battery of 15 kilowatts. Back-to-back converter that's new, 104 kilowatts. We've got few EV charging posts. Right now it's free, we are planning for more. The reason we have them is we have a Nordic Electrical Vehicle Interoperability Center at our premises. And we check both, we've got providers from Nordic countries for the charging posts. And then we check if plugs fit and also if the communication between the car and the post is interoperable. That's why we have those charging posts, but then we can also connect it to our grid and then play with the electrical cars. We've got 2 electrical cars. One is running and operating, one is not running. Yes, we are working on it to make it run. It's a Toyota Prius that we changed from hybrid to plug-in hybrid, but it's not working now. We've got a machine set of 30 kilowatts, and we've been testing batteries for one of our projects, and therefore we have a free testing base that we have inverters inside, so we can play with those as well. And these are facilities that are spread over, well, what is the distance? About a kilometer, yeah, around. We have this in our entry hall to our building. We could see the live data from the system. That's a grid. We have free grid connections. We are either buying or selling. We've got 2 wind turbines, 3 solar stations, a diesel generator, flex house, which is the office building, storage, different batteries, EV posts, and dump load. And here we can see overall production consumption of the whole SUSLab, grid exchange and storage. So we can see everything what is going on. So if we everything is, we've got a remote control over everything, so we don't have to actually go to facility, but if we run some experiments, we can sit in a chair and look at this, this graph, if anything is working. And there is another display on our wall. This is not very easy to understand at first glance, but these are the different buildings that we have. These are the charging posts that we have. And because we want to have a reconfigurable system, so we have different cables and bus bars. So if something is connected, then it's red. If it's disconnected, then it's white. And we can create different topologies from this static system with copper wires. And this is just a view of how it looks at the moment, so how your experiment is set. You have to learn how to read from it. It's not so easy. We are planning on improving this, making it more readable. So what do we think that our facility is good at? We can test system control concept. So we can test different VPPs, microgrids, isolated or grid connected. We could look into agents and distributed control. We also work with demand response, especially with the household demand response. And we could also look at the communication in a smart grid. What we also do is we've got different components that we could combine them in a different way and see how they interact with each other. So what do you get if you have a wind and solar and a storage in the system? And you could observe that the wind is quite variable, and then maybe you could use the battery to make it more smooth if you want to feed it, for example, to a house. You could have this kind of system. And we also test components. The components that we have or components that we get for different projects. And we make models of them and determine the properties. For example, the battery that we got, the vanadium battery, we tested that is actually, it has more capacity than the documentation says, but it's for security reasons, we cannot use it. We have to make a sophisticated controller to use the full capacity. And the way we would like this lab to work is to get a component if we buy something or get something and just plug it into the power system easily. Now we are part of one of the Danish projects that is part of a strategic platform for innovation and research with intelligent electricity, and it's Danish grid. We're looking at. We understand that we have to switch from consumption-driven grid to the production-driven grid because we cannot control the production. But in order to do this, we have to change many aspects of the smart grid. So we have to look at the domestic and commercial demand response, how the factory demand response would look like, and how the household demand response would look like. What would change in distribution grid operation, in the control and market operation, what is the socioeconomic influences on all of this, and how how users would react on this smart grids, because we've been assuming that the user will just be super happy and say yes, we want to participate, but actually there've been some research done that it's only in Denmark. They tested the Danish society, and they discovered that there are enthusiasts, people that don't really care, and skeptics. And they removed the extreme cases out of the study because it's not interesting, it's just few people. And they discovered that people are very motivated by price, but in Danish society they're also very motivated by green tag or things. It's like when they buy ecological food, it's more expensive, but they know that it's better quality, is produced in a fairer way. So they're happy to spend more money on the product. So they're also happy to do the same with the energy. If they get a stamp on their letterbox that they use green energy, maybe they'll be more happy. They could show off to their neighbors. But that's just a study in Denmark that was done. And yeah, so what consumer is doing. And socioeconomic and investor evaluation. Okay, so a business case, yeah? You know, okay. Okay. Okay, so it's a quite a large project that is trying to do a lot. It's 32 partners from industry and universities. It's mainly Danish. We've got some partners. We've got some collaborating universities from US as well that would like to watch what we are doing and maybe help us a little bit. Okay, that's the project. Okay.
Just a small question.
Yeah.
So the goal, could you go one slide
Yeah,
back?
I'm trying. It's yes, not so fast.
The vision is to develop an intelligent power system. So are you trying to replace the power system of Denmark, or is it a showcase somewhere where you can demonstrate it?
It's
or is it a platform to analyze it?
It's we don't want to change that much the physical part. So
well,
what?
How large is it? How large is the power system that you are developing?
Help me out, Oliver.
I mean, it's technology development. So I mean, this is technology to be eventually deployed in the Danish power system. And there will be demonstrations in iPower as well, but it is not. The idea is not within the iPower project to change the Danish power system.
Yeah.
It's a technology development.
So develop technology and principles, and then they can be used.
Yeah.
So we can reach the goal of 2020 of 50% of wind power without adding more generation. Yeah. Okay, back to SysLab. As I said, we are in 3 buildings. So we've got 3, we could call it small substations that are located close to different buildings. And we can organize the system as one large system or separated small systems that work in parallel, so we could run a few experiments in parallel. And we could make it isolated or connected to the public grid, which is, we have a connection in every building. So then we can compose it, and it's all remote controlled. Now the hardware platform for software that we have, in every unit we have a box. So for example, for wind turbine, we have a box that consists of a computer, measuring device, network equipment is a switch, and then some backup power and field buses that are connected to actual unit. And all of these nodes can communicate with each other. There is no central node in the system, so it only consists of all the nodes that we have. There's no central place. So the system could be run and controlled from any node or from additional node. It doesn't matter for us. And right now we have 21 SysLab nodes and 20 helper machines, for example, for visualizations. And in total, the source code is around 1,000 files, but it's growing. And what is on the machine? The code is mainly in Java. There are very, very few C files, just for very low drivers, exactly to the machine, so we can control them. The interaction is through Java RMI services, which is the remote method invocation, and invoked over internet links. I'll explain it. We've got 2 machines. We've got RMI server on one and RMI client on the second one. And if you would like to revoke some method on this machine, you can contact this server and ask, please run this method and return the result to me. But it's actually run on the different machine. So, the machine could expose the interface, the RMI interface, to all the units and say, I would run these functions if you ask me to. And this is how we interact between different machine. Yes.
Do they know each other? Do the nodes know each other?
You have to provide the name and location, and at this point, yes.
Yeah, I know.
That's when we get to the platform thing.
Okay.
We have some tools based on Jaxter, where nodes can give themselves tags and then find other nodes with other tags and something like that. But yeah, that's just some experiments we put in there.
But
for a lot of the experiments, we're simply like a lot of the projects that are running right now, they do central control, which we're not really happy with, but that's what our funding bodies or our collaboration partners want. And then obviously you set up a central controller that knows the nodes. But we've been doing experiments simply with node discovery and so there's some infrastructure in the platform. It's not as far as we would like it to have.
But if you know if you know what is in the interface, then you can invoke it. At least it's this, all the infrastructure down is done. So all you have to do is but then you have to implement discovery and yeah. Okay. Well, how is the units represented? What we have now is that the similar units are represented similarly. So both wind turbines appear to be very similar. But the drivers are of course different because they are different machines. And what we would like to have, what we are going towards to from different directions, with different ideas, is that the devices that provide the same service would be described the same. So if you would like to, if you are a producer or a consumer, you would be described the same, or even more power system services, like all the units that are controlling frequency would appear identical to the higher levels of the control. And then the type of the unit is no longer important, but this is what Oliver was talking about as well, with the service-oriented architectures. Yes.
One back, please.
Yes, it's doing.
In IEC, there is some activity in representing distributed energy resources based on IFC. Are you using that?
Not at the moment, but IFC is for buildings, as I know. Yes, and it's describing actually, as I know IFC from building automations, they describe where is wall, is there a window on the wall.
That's a BIM, that's a building information management system.
But IFC as well. IFC as well.
Yeah, it's based on IFCs, but there is in IEC, there's working groups that do IFC classes for transformers, wind turbines, all the elements there.
Yes, that's
harmonize it with 61850.
Yes.
Can I interrupt? If you use 3 different abbreviations in one sentence, I will not understand because I'm not close to any of them.
IEC is International Electrotechnical Commission, so there's a standardization body. No, I'm following working group 17, so I've been to the last couple of meetings. What the reason I'm going there is to promote this idea of not because. If you look at, sorry, we have a short nerdy argument, but
we can do it over here, then it's allowed.
Yeah, in 6150-7-420, that is exactly what I was talking about earlier. That you have the units separated by type. You have data models that are specific to unit types.
Yes, it's old-fashioned.
It's old-fashioned. I mean, it's in the history of how the standard evolved. This is quite natural that it went there, and there is some. For example, there's this new inverter representation. Report 19-8, I think it's called, that actually looks at making generic interfaces for units so that all units that have an inverter like PV or electric vehicles or something like that, they would be represented similarly. But to me that doesn't go far enough yet.
Yeah, it's extremely slow. I mean,
that's and they have a lot of problems even describing them, and they're arguing how you should describe this or that.
It's a mess. So I was just asking in the mess.
I can also supplement a project 2 years ago that was making some, maybe I should, for those that are not in so deep in power systems. There's a standard that came that's about 10 years old, I think roughly. It's called IEC 61850. Remember that number because it's gonna pop up in smartgrids at every corner. And that was because traditionally in power system control or power system communication, you had sort of proprietary binary protocols that you know, like from the dark ages of computing, and that was sort of the first effort to make an XML-based, generic, non-vendor specific representation of some power system components. Right now, that is adopted by some manufacturers, and that is being sort of touted as something. It's the last word on communication between smart components and controllers. But yeah, that is some of what I said earlier in my presentation. Is there's some, I think, criticism that you can put to the standard, but it doesn't. It's actually not very well suited to.
Service-based.
Yeah,
because
So
the
implementation,
yes.
to aggregation, to yeah. So.
That's correct.
Yes, coming back to the question. Maybe I'll come here. It's we have the ARMA interface, which is a little bit type-based. What we would like to have service-oriented. Then we would like to use ontologies following the 61850 and maybe describe the services with all S, because it's an already mature language of representing services with ontologies. And it's used in the World Wide Web, so maybe it's a good idea, maybe not, I'm not sure. We will try it out and see how it works. And in the iPower, in the project that I just presented, they came up with a flexibility interface, which is an information model for describing actual flexibility of the unit. So how flexible it could be. So it's another look, another view on the service from the unit is the flexibility. So how can you shift, how much can you give to the power system. So that's another approach. And maybe I'll explain what is, how do we control units. There are two types of control that are well known. It's direct control and indirect control. Lately it's been a problem to distinguish, because the systems get so complex that it's difficult to say is it actually direct control or indirect control. But in iPower we've done some research, and we came up with a distinction that we think is right. Yes. And therefore we define direct control as controlling the unit directly, that you know how the unit is going to react. So you ask unit for a service, and then the unit would reply, yes, I will do it exactly like you asked me to. No, I'll not do it at all. Or I can do it, but I have a condition. So it could be some negotiation. But in the end, the controller and the unit know what is happening, and especially the controller know what kind of service is going to get and how exactly. When the indirect control, when the signal is sent and the request is being done, the unit will decide by itself and will not inform back. It's here's something similar to the environmental condition. It's like